already we have seen the bagging technique. Just in the previous lectures, we have seen the random forest. This is the most popular algorithm for a bagging technique in the series of ensembles models. So bagging. So the most popular one for this bagging is random forest. Already we have seen in the bagging technique, we have a high variance model, plus low low bias model, high variance and low bias model. We have taken this thing as a base learners. We have taken this thing as a base learners model. Okay. As a base learner. Plus, to reduce these high variances, we have using some sampling technique, randomization sampling technique. We have using here randomization sampling, that is column sampling plus row sampling. Okay, that's thing. And also here we are using, after building the base learners, we are using the aggregation technique. We are using the aggregation technique. Okay, so this thing we have used to reduce the variances. This is the simple the bagging technique for the ensembles model. Okay, now for a boosting technique that are going to discuss, boosting technique. So in boosting technique, we have taken the base models, for the base models low variance and high bias. Here we have taken high variance, low bias, but here just opposite of this we have taken here for the boosting technique as a base learner model. So here for a base learners, we have taken low variance and a high bias. This thing we have taken for a base learners. So now our main job is to reduces the bias system. Okay, so how do we reduces the bias system? By simple using the additively combined technique. By simple using additively combined technique. So additively combined to reduce the bias while keep our variances as low. Okay, actually for base learners we have taken the variances is low and we have taken the bias is high. So to reduce the bias, we have additively combined. We have using the additively combined technique to reduce the bias, but we have to mind this thing that while we have to keep, while we are keeping in variance, our variance as low. These things we have to to reduce the bias that does not affect to increase the variance. Okay, so just using this technique, additive combined technique, to example we are build the boosting model. Okay, so the most popular boosting model is The most popular one is gradient boosting. That thing we will learn in the next part of this video, next part of this series of lectures. So now the best popular one is the gradient boosting algorithm. Okay, now if you just remember the generalization error for a model, so the generalizations error or simple, if you just call the error term, the error performance is depend on the bias square plus variance plus some epsilon value plus some epsilon. These three things as depend on the called the generalization error. These three things is called the generalization. Here our bias is low. Here our variance is low. Here variance is low. So there's things we have low, but the bias is high. So now our main job is here to reduces. So the main job is here to reduce this bias. Main job is here reduce the bias. This is the main job here. Okay, this term is called the generalization error. Now let's discuss the core idea behind this boosting technique. Core idea. What is the core idea? So now let's discuss step by step. What is the core idea behind this? The core idea is that first we have to the main target to build a boosting models. Our main target is reduce the bias term. The main job is reduce the bias term. This is the main job we have to do. So already we have discussed some classifications algorithms, some regressions algorithms. They have some models, those who have some high bias and low variances. Already we have seen this thing. So we have already discussed some classifications algorithms, some regressions algorithm. That's thing already we have discussed. And a high bias and a low variances is model is example of high bias low variances is an example of decision tree which has depth is very shallow. So such kind of model is a high variance, high variance high bias low variances model. Okay, now let's see these things step by step. Okay, suppose let's take first our training data is look like that. Suppose let's take our training data is train is our set of pair of values xi, yi, and our I from 1 to n, where n is the number of data points in our training data set. Okay, so suppose let's take this is our training data sets, and first we have to build first job we have to do. First job is using this training data. Using this training data means xi, yi, I is equals to 1 to n. Using this training data, first we have built a model. Suppose let's take I am using here first the the intuition of this lecture is intuition behind the boosting technique. This is the main motto of these lectures. I am not to discuss the examples of some boosting algorithms. I am just giving you the concept how the boosting algorithms actually work to build a model. So this is the main motto of these lectures. Okay. So suppose let's take this is our training data xi, yi. This is our training data, and using this data we have built a model. First we have built a model m0. Okay. First we have built a model. Suppose it is just for simplicity I am using a, instead of 1 I am using a 0. Okay, because of some indexing. because of some easy of our indexing, understanding some indexing. Okay, just I am using first in step 0. First I am step 0 in initial, means it's initial stage, that is called initial stage. Initial stage. Okay, I am building the m0, and this m0 means how much, and this what kind of model this m0 is. This model is simply high bias model. This is simply high bias model. Okay, and as well it is a low variance model. So as an example, if you consider as an example, this is decision tree, which is shallow depth. Already these things we have seen in decision tree series of lectures. Okay, so this is the sample. In the first initial stage we have to do this job. Okay, so these models we have high bias, and high bias means what? Actually high bias means what? Just to recap this thing, high bias means what? High bias means we have the large training error. This is simple. If we include, to build a model, if we include the bias term, means what? Actually the training error of this model is so high. So this is a large train error for this model. This is the large training error for this model we have. Suppose let's take the model m0 is look like that. Suppose let's take this model, the functions of the model is y is equals to h naught of x. This is the simple mathematical formulations of this model's m0. Okay, now first we have to do this job. First we have to do this job in the sub stage of the stage 0. The second sub stage we have to do the find the error term. So actually for this is the yi is actual term. Actual output for this means actual output. Just I am using another different color for better understanding. So this is the actual output for the data xi, but our predicted output is what? But our predicted output is h naught xi. This is the predicted output, and this is the actual output for this data xi. Okay, and the simple difference of this is called the error term. This is difference called the error term, error I. Now this error is called the simple difference error. This error is called the simple difference error. This error is simple called the simple difference error. And also we have seen there have in logistic regressions, in linear regressions, in support vector machines, in some there are various kind of errors we have already seen. So such like that we have already seen in square error terms. We have already seen the logistic loss means logistic error. That's both the same thing. Logistic loss means logistic error, and also we have seen in hinge loss means hinge error. So for the simple set here we are using the simple differences error for the simple differences. So now our data sets will be look like this. So here we have xi yy. Now by calculating this error term, now the data sets will be look like this. Xi yi. Also we have calculated here the error term for each data point error. Now our data sets is look like this type at the initial stage. Now okay, this is the simple the initial stage that we have to do. Now in stage 1, now in the next stage what we have to do in the next stage, that is stage 1. In the stage 1 now we are built the another model m1. Now we have built the another model Suppose let's take here in this stage we have built another model M1. So how we will build this model? We will build this model by using this data xi, error I. Okay, here in this stage we have not considered this yi value. Here we are just taken this error I value to train this to build this model M1. Sorry, it will be M1 in stage 1. M1. Okay, so suppose let's take this M1 is, suppose let's take this M1 in H1x. This M1 is H1x. So H1x, if you just if this model is H1x, if we use H1x xi, if we just use H1xi, this means what? For the error term, this is means predicted error term, for this data set I, predicted error, and original error we have, this is equivalent to, suppose let's take H1x. This is the predicted error I. Okay, and this error I means what? This error I means this one yi minus h0 xi, yi minus h1 xi. Okay, these things actually are predicted error. All the things are not equal actually. By we are built from this data, we have built this model M1, that is the predict our error that comes from our initial stage. Okay, so M1 doing these jobs. So the H1xi now is the predicted error for the stage 0, for the stage 0. So for the stage 0 error is this one, and these things is the predicted error. Okay, I think you have understand how the M1 is actually doing this job from the data from the initial stage, that is stage 0 here. Okay, so now after building this, we have build the model f1. Suppose let's take this is the f1x. That's models we have built at the stage 1. This is the simple stage 1. This is the simple stage 1. So here we have building the model at the end of stage 1. We have built this model at the end of the stage 1. Now in stage 1, if you just internally look like our this f1x is actually look like this type of models, means we have some value there have, suppose let's take alpha naught h0 of x plus some value alpha 1 h1 of x plus this one, these things. Actually after stage 1 we have built this kind of model. Okay, and if you look like internally, these models actually look like weighted sum of the two base models. Actually base models is what? Here h1x means model M1, and h0x means model M0. And if you just internally do this is the simple weighted sum of the two base models. This is the simple weighted sum of two base models. Here base models, what? Base models M0, M1. This is the base model. Okay, at the end of the stage 1 we have built this model, weighted sum of the two base models. Okay, f1, that is built from the end of the stage 1. Now let's come to the stage 2. So now what we are doing after the stage 1, we have the data sets look like that: xi, error I, Now by using this data, simple we have using the next model m2. M2, suppose let's take this model is h2 of x, h2 of x, okay, and this error I means what? This error I means yi minus that's come from our previous stage, yi minus h1 of xi means, sorry, this come from the previous stage means f1 of xi, f1 of this error I used to look like that after the stage 1. And by using this data, we have built the M2 model. That mathematical formulations is H2 of X. So after the stage 2, the same thing that we have doing in stage 1, the same things also we have doing in stage 2, also doing this thing in stage 2. So after this end of the stage 2, what our models is look like that. F2x, that is the weighted sum of plus alpha 1 h1x plus alpha 2 h2x, look like that. At the end of the stage 2, the same things. So the thing is repeatedly doing. So suppose let's take, we are repeatedly doing this to iteratively doing these jobs, and at the end of the stage, suppose at the end of the stage k, what we are building our model after end of the stage k, our models which look like if k of x, this is simply I is equals to 0 to, suppose let's k alpha I hi of x, okay. So this is the after end of the stage k, our models is look like these things. So because of these things, we call these models is additive weighted model. Just see this thing. Additive means we have taken the summations. Weighted means for each base models we have taken some weighted value alpha I. Because of this, we have taken the models is additive. Additive weighted model. It's because of these things. So simple here, these things hi of x, these things are doing this job. The job is we have trained to feed the reducible error. These things is actually in so what hix. If you just see these things, hix, these things. Actually, hix means what? Error. Just we have to predict the error. The job is hi is to predict the error, and error is simple. What the residual error means? That error come from the previous stage. In these models, we are trying to reduce it. Okay. So the model is trained to this model. The job of this model. Better if we're using this word. The main job of this model is trained to fit the residual error at the end of the previous stage. So the main job of hi is this, to train the model that reduced the residual error at the end of the previous stage. Okay. show the HIX. Just to write this thing again. So the job of HIX is how to build this HIX. HIX sample build by using this kind of data, and this error means the sample yi minus that's come from the previous stage, yi minus 1x. And this error is another language is called the residual error. This error is another language. It is called the residual error at the end of the previous stage means stage I minus 1. Okay. So what we are getting from here? So we are getting, just to recap these things, we have getting after some stages, after some, if we consider the k stage, after some k stage we have built a additive weighted model, that is fkx. Fks, this is sample I is equals to 1 to sample 0 to k, and alpha I hix, so here the main relationships is age models is dependent on the previous model. So if we build fix, and these models is depend on the to build the next model, the next stage. These models is depend on the to build the next model. So age models is dependent on the another model. Age models is dependent on the another model. This is the job, iterative job that we have doing. So if we increase the value of k, the advantage is that if we increase the value of k, then ends at the end of the iterative process, we have a lower residual errors. So at the ends we having a lower residual error. We have a low residual error. Means what? Low residual errors means what? Actually this error means training error. We are interested to minimize, actually just to recap these things. Actually we have a high bias models. If we have a high bias models, means we have a large training error, and our job is to reduce the this large training error, and by sample using this technique, boosting technique, we have minimized the error term in the eighth step. So our job is at the end of the case step, our job is we have low residual error. Low residual error means we have training error is reduced. Our training error is reduced. Okay, this means what? This means our bias is reduced. Our bias is reduced. That's thing, that's job are actual internally, the core idea, the actual job actually doing this step, this process, the boosting technique. Okay, I think you have understand the main intuitions of these lectures, how these boosting techniques actually internally work this thing. I think you have understand this thing. Okay, so now the best popular of the boosting technique is, so boosting technique. So the most popular one is gradient Boson decision tree. Gradient, that we will see in the next lecture, next part of the lectures. That we will see this thing. Gradient boosted decision tree, and these things are actually built. These things are actually build a low latency model. actually used to build a low latency model, mainly in internet company. Okay, and the another one is the adaptive ADA boosting technique. The all the things we will see in the next in this series of lectures, all we will see in the next part of this lecture, ADA boosting technique. So the main job means the applications of this ADA boosting technique is for face detections using images for a face detection. This ADA boosting technique is mainly used. Means face detection means this technique cannot say the what which face it is. These things, this suppose let's take it's a image. This ADA boosting sample call the here it is a face, here it is a face, here it is a face, here it is a face. Just it is job is the main job is detect the face, but it cannot detect actually which face it is. Just it's tell that this is a face. Okay, the main application. So we will see in applicative point of view the ADA boosting technique, and in details explanation the gradient boosting in the next part of this lecture. Okay, I think the main intuition, the main motto of these lectures are clear all of you. Okay, so we'll see in next lecture.